Now that we've measured the voltage across all of our components, in particular the CSR, we can not only determine the loop current, but we can also determine the power in each of the four components. So since we have a negative 0.27 volt measurement across our 100 ohm resistor, we ended up with a negative 2.7 milliamps as our loop current. So if we take that negative 2.7 milliamps and we multiply it by our positive 8.42 volts, we end up with a negative 22.7 milliwatts. The negative 2.7 milliamps times our negative 5.343 volts gives us a positive 14.7 milliwatts. Negative 2.7 milliamps times negative 2.7 volts equals positive 7.3 milliwatts. And our negative 2.7 milliamps times our negative 0.27 volts across our CSR equates to 0.7 milliwatts. So that's a positive. So Kirchhoff's laws not only apply to voltage and current, but they also apply to power in a circuit, meaning that the power measurements in each component must sum to a value of 0 in the circuit. And it does in fact work out. If you add up 0.7 milliwatts, 7.3 milliwatts, and 14.7 milliwatts, it equals 22.7 milliwatts. But you'll notice that their polarities are opposite. So the power supply always, as I've been stating for a long time, power supplies compute to a negative power because they are sourcing power to the circuit. Any component that dissipates power will measure or compute to a positive power. Okay, we're back to our original diagram again, but this time I've added oscilloscope probes to the schematic because for this example we're going to be interested in measuring the battery power. And just to refresh our memories, in order to measure the power of a component, we need to measure the voltage across it and the current through it. So in this case here I have the channel 1 probe, the positive probe on the positive side of the battery, and the ground lead of channel 1 is on the negative side of the battery. For our current, we need to measure across our CSR, and I'm using channel 2's positive probe is on TP3 here, and we've got the ground lead of channel 2 together with the ground lead of channel 1. Now we need to, normally most of us don't have expensive current probes and we don't have isolated channels on our oscilloscopes, so that forces us to have to common the ground leads of our oscilloscope, and that's why we tie both the channel 1 and channel 2 ground leads together here at this common point. Now we actually have a slight problem with this, and if you haven't already observed it, let's review how we measured this circuit with our voltage meter. So we started out across the battery, like so, positive on the positive of the battery, and we moved around the circuit in the direction of the current flow, like so, to measure the 2K resistor. Then we measured the LED, like so, and then the CSR, we ended up measuring it like this. Now you'll see that the probe terminals are actually inverted now, according to our oscilloscope configuration. We should actually have our channel 2 ground here and our channel 2 positive here. But we know we can't do that because of the ground isolation problem. So we in fact have to invert our CSR probe when we're making oscilloscope power measurements. So it's not a big deal. We can deal with it as long as we are aware that our current channel is actually inverted. Now the easy solution to this, in order to retain the proper phase of our power measurement when we finally get the oscilloscope to compute what the average power of the battery is, we can simply use the invert function on the oscilloscope to invert the polarity of the channel 2 probe. So it effectively is like switching the probes around so that our positive is here and our negative is here. We physically can't do that because of the isolation problems, but we can do it electrically inside the oscilloscope and we have the same effect. So when we invert the channel 2 current probe, we will in fact, when it multiplies by the positive battery voltage here, we will end up with a negative power, just like we did when we computed it with the calculator.